Greetings, all. I hope this video finds you and your family safe. This is an unprecedented time in American culture, so hopefully you're following some rules, being safe, and keeping the social distance and the like. As far as getting back this semester, I doubt that's going to happen. We're going to be online for the rest of the semester, I believe. They're talking me through it, but I don't think it's going to happen. Anyways, brand new chapter, brand new topics, brand new everything. Going back to our exam with chapter 4. You guys all did very well, which I was pleased with. But the fact is, we covered most of that material while we were in class. So from here on out, it's going to be all these PowerPoints, these voiceovers. I've created a lot of videos. In fact, right at the very top here, you want to see a listing of all the videos that I've created. Here's my YouTube channel. There's the URL. Now you're going to see some videos that deal with college algebra as well as statistics. You can figure out which ones. They're all labeled just the way they are in the PowerPoint. So check out the channel. Chapter 6, Normal Curves and Sampling Distributions. I want to start out with a couple of definitions here. I'm going to say, well, gee, why is he doing this? Well, the idea is when we're studying any subject, it's just not a matter of, here's the calculator, plug these two numbers in, and here's the answer. We understand why we're doing what we're doing. That's education, knowing what it is you're doing and why you're doing it. Quantitative variables, a random variable that value x takes on in a given experiment. X could be, hey, what's the probability that exactly 4 or the probability that x is greater than 1.2? X is that random variable. We don't know the answer, so it's a variable. Random meaning it could be the answer could be anything. Two types of random variables. Discrete random variable can take on only a finite number of values. It's a counting number, like 1, 2, 3, 4, 5, and so forth. Continuous random variable basically has the capability of being some decimal, like 1.56 or 2.348. All right, the distinction between discrete and continuous is important because of the different mathematical techniques associated with the two kinds of random variables. All right, number of eggs that a hen lays. It's discrete. Why? Because that hen's not going to lay 2.34 something eggs. Could be 0, 1, 2, or 3, or 4, so forth, up to, I don't know how many eggs does a hen lay in a day. It's a counting number, right? Discrete, as opposed to the amount of milk that a cow produces. Could a cow produce exactly, 7 quarts? Yeah, but no. Chances are it's going to be some decimal, 7.43. If depending on the scale, the way you're measuring, it's not going to be an exact number. It's going to be, it has the capability. A continuous random variable has the capability being some decimal, whole number with a decimal, just a plain decimal. That's the major difference. And there it is, discrete random variable, finite number of values, 0, 1, it's a counting number. Continuous random variable has the possibility of being a decimal. All right, so there's an idea here. You get the counter, it's going to be discrete, all right, whole numbers, counting numbers. In fact, actually, I'll call it whole numbers because 0 is not a counting number, it's a whole number. Whereas this voltmeter, the voltage could be anywhere from 0 to 9 on a continuous scale. A number line, all right? That's the difference. These are some questions we had back in chapter 4 and chapter 6. A test consists of 10 true false questions. What's the probability? At least 6. This one talks about the probability of no more than 6. This one here is fewer than 3. Among 13 adults, what's the probability at only 3? Notice all these problems we had in chapter 4 and chapter 5 in probability dealt with whole numbers, counting numbers. I want to say whole numbers, all right? Because sometimes we didn't with 0. There wasn't any decimals, all right? You can't have 6.32 kids or 5.2 physics majors that were ethnic minorities. All right? They were whole numbers, counting numbers. If you include 0, you got a whole number. Counting numbers start with 1. Get the idea, no decimals. Look at what we got in here. Starting, this is actually section 6.2, very similar to section 6.3, actually. Doesn't mean when you have a continuous number, a variable, that it can't be an exact 53.0, but it has the capability of being a decimal, like greater than 15.2, greater than 16.1, greater than 17. Well, 17 is a counting number, and that's good. I mean, the idea is here again, it's got the possibility of being a decimal, like a number five problem here between 19.7 and 25.3. The idea is we didn't see numbers with decimals. We didn't see these continuous types of numbers in previous sections. So that's prompting us to do these problems a whole brand new way. And how we're going to accomplish this is by this normal distribution, this bell curve here. Now you're going to be drawing it. For every example, pretty much, you're going to be drawing this bell curve. If you're trying to do these examples in your head without drawing a bell curve and marking off what it is you're looking for, what area or what Z or X score you're looking for, you're, you're setting yourself up for trouble. Drawing this curve is no big deal. You're going to draw it a lot of times. And I'll be doing it as we move on. Here's the deal. I tried as best I could to actually, I can get this video embedded to play, but with the software Screencastify, as many times as I tried, it won't play the sound. So here's my suggestion. As you're going through watching this video of the PowerPoint, all right, also have the actual PowerPoint on your desktop. As you're going through it and you want to play this, go actually to the PowerPoint, click on the arrow and it'll play. All right. Now, many times it's going to go to YouTube, and if you want to see it full screen, click on the YouTube icon or bring it to YouTube, and then you can display it full screen. All right, but this will not play here because you won't hear any voice. All right, so go to the actual PowerPoint. In fact, what I'll do is I'll upload a PDF version just in case you don't have PowerPoint. Folks at Massasoit, you have access to it in Canvas. It'll play right out of Canvas. So you can download Microsoft Office. For those that don't have Office, I'll also post this as a PDF. But this will not play right now. Play, but you won't hear any sound. So stop it. Go to the actual PowerPoint, not the video of it, but the PowerPoint. And click on the image. Now there's going to be a lot of videos, so you're going to have to watch it and play the videos. Why we can use this bell curve to figure out probability is this formula right here, which is actually something in calculus. All right. The deal is, suspiciously enough, all right, the area under this curve is exactly one. Now, if we recall, the probabilities of all the elements in a sample space equals one. All right. Probability always adds up to one. So this area being exactly one allows us to use and find probabilities. Probabilities are going to be associated with areas that are under this curve here. Now, for a proof, you can click on here again in the PowerPoint, not here because you won't hear the voice. There's a proof of this. And here again, you're saying, well, why am I doing this? I want you to know why it is things are working out. So just buying what I say, well, this is the way it is. No, you need to question things sometimes. All right. So the video proof, you never have to remember this formula, obviously, but I just want to show you why it is that we can use this curve to figure out probabilities. Probabilities will be associated with areas under the curve because the total area under this curve is exactly one. Normal distributions. I got two graphs here. One is a relative frequency and one is not. The idea of a bell curve is that here it is. You have low points. You get to the mean, it's the highest point, then it comes down. Bell-shaped curve. Now, that means it's exactly, but it's pretty darn close. All right, as opposed to things that are skewed. Once again, you can watch this video, and all it's talking about is a left skewed data that represents the left skewed in the graph, data that represents a right skewness. Check out the video. It just gives you an idea. An example of a right tail skewed, incomes, right? Most people making between, $30,000 and $40,000, and then it tails off. We got a few people here, math teachers at college. Something that is left skewed, all right? Heights of students, very few kids, tiny, and then it peaks, and then you find very few people that are extremely tall. This is a right student. So, all right, but we're going to be talking about normal distribution, bell curve. Suppose Tina and Jack are in two different sections of the same course. Each section is quite large. Scores on the midterm exams of each of the following were normally distributed. All right, Tina's section, the average, the mean was 64. She got a 74. Jack's section, the mean was 72. He got an 82. Both Tina and Jack were pleased with their score. I got a feeling that Jack was a little happier. But anyways, he says each student was 10 points above the average. However, the fact that each was 10 points above the average does not really tell us how each did with respect to the other students in their class. And this is a situation because we're going to be presented with all types of problems with different means and different standard deviations. We've got to find a way to standardize this. And we're going to do it is what's called a z-score. In either case here, here's Jack's section. The mean was 72. Jack scored an 82. Here's Tina's section. The mean was 64. And her score was a 74. All right, now notice the figure is missing here, but the standard deviation in Jack's class was 10, and the standard deviation in Tina's class was 5. So it looks like Jack is one standard deviation away from the mean. And Tina, even though she had a lower score, she was two standard deviations because her class average was only 64. So in actuality, Tina did better in relation to everybody else because her score was two standard deviations. Notice if one standard deviation is 5, her score's out here at 74. She's two standard deviations away, Jack. Here again, I mean, Jack's happy he got a higher score, and Tina can brag, well, relative to my class, well, all well and good. All right, standard deviations. I'm sorry, changing a raw score to a z-score. What a z-score is doing, it's telling us how many standard deviations that score is away from the mean. What this is going to allow us to do by standardizing scores is to use one table. Now, granted, the calculator is going to bail us out like it's bailed us out every time before, but there'll be times when you're going to have to use these tables. In fact, it's called Formula Carded. I've uploaded it onto Blackboard into Canvas. I suggest you download that file because there'll be times when you're going to have to use the table. In fact, going through this, I show you several examples where we do use the table, and then I say, okay, let's cut to the chase and use the calculator. All right, z-scores. How many standard deviations is a raw score away from the mean? And there it is, a simple formula. You take your raw score x, you subtract the mean divided by the standard deviation. All right, what does it tell us? A standard score, a z-score of measurement tells us the number of standard deviations. I just said that. All right. A positive score tells us the measurement is above the mean. A positive z-score. A negative z-score tells us the measurement is below the mean. Now you got to recall, z-scores and raw scores can't be positive. They can't be negative. Um, but areas obviously fall between. Areas relate to probabilities, and probabilities are always positive numbers. So don't get confused. Areas will always be positive. Z-scores could be negative, could be positive. Areas will relate to probabilities, and you can have a negative probability. They run from 0 to 1 inclusive. This is going back to like chapter 2. All right, so there's Jack's score. All right, his Z-score, his raw score was 82. The mean was 72. Standard deviation of his class was 10. His score was one standard deviation away. Tina's raw score was 74. The mean of her class, 64, divided by the standard deviation of the class. Notice in relation to her class, she did better because her score was two standard deviations away. Doesn't mean much. Jack's still smiling. He still got an 82. All right, heights and weights are measured in different scales. You know, heights are measured in inches, feet in inches, weights were measured in pounds. So here's what we want to know. Which is more extreme? Someone who's 76.2 inches tall or someone who weighs 237.1 pounds? We take these two because they are different scales. We want to somehow standardize it so we can compare it and find out, hey, which one is more extreme? Which one has a larger z-score? Well, taking the raw score, subtracting the mean for all, I guess it's men, Their height 68.34 divided by the standard deviation of all men. A height of 76.2 has a z-score of 2.60, whereas a weight of 237 based upon the formula here, the raw score minus the mean of all men, 172.5 divided by the standard deviation of all men as far as weights. That z-score works out to be 2.45. All right, since 2.6 is bigger than 2.45, it's more extreme. All right, that someone, it's more unusual, I'll say. How's that? That someone's going to be that tall. 76 inches, let's see, 6 foot would be 72, so this person's like 7'6'4". And height of 230, weight of 237. We're a larger society. As a rule, anything that is greater than two standard deviations or less than negative two standard deviations is considered unusual. Anything between, in this range here, between negative two and positive two is called ordinary values. Things that are greater than two is unusual. Once again, I guess in both these cases, it would be unusual to randomly pick somebody who's 6'4" and also randomly pick somebody out of a crowd that weighs 237.1 pounds. All right, so it'd be a futile task to set up a table of areas under a normal curve for each different mu and standard deviation combination. We have 15 problems. They all got different means, all got different standard deviations. We need a way to standardize these distributions so we can use one table of areas for all normal distributions. All right, so once again here, this is a standard normal. Now, a standard normal, interestingly enough, the mean is 0 and the standard deviation is 1. That doesn't really happen. That's kind of a make-believe situation, but it allows us to use this one table. We're going to take all of our different values and standardize them. But here's what's really powerful here. What's powerful in a standard normal, because the mean is 0 and the standard deviation is 1, when I translate to a z-score, I take the x-score, I subtract the mean, I divide it by the standard deviation. What ends up happening is that my z and my x are synonymous. Well, that makes my life real easy because when I do use this table, I don't have to do any conversion. Whatever raw score they give me, an x-score, it's the same as a z-score. Because once again, using the formula, subtracting the mean divided by the standard deviation, x minus 0 is x divided by 1, z and x are synonymous. The thing I want to point out is when we go out to infinity or negative infinity, I want to show you on the calculator the key that you use to signify negative and positive infinity. It's the second function of the comma key followed by a 99, which means 1 followed by 99 zeros, or a negative 1. A negative 1 followed by 99 zeros. Well, a 1 or a negative 1 with 99 zeros, that's a fairly large, it's a huge positive number or a huge negative number. I'd say that's infinity. What ends up happening here, if your raw score is bigger than the mean, you're going to have a positive z-score, and if your your x-score is left of the mean, your z-score is going to be negative. All right, to the right of 0 positive, to the left of 0 negative. That's all this line is saying. What's interesting about drawing these diagrams, many times you'll look at the answers, and just by looking at your diagram, there's going to be two answers that make absolutely no sense because you're going to compare it to what you've gotten. We know that if I were to draw a line right down here, I've got 50% of the area to the left and 50% of the area to the right. That's going to be helpful in stopping you from making some careless mistakes. All right, so table A2, you have a positive z-score table and a negative z-score table. That's in the formula card. All right. This is what's called, our table is what's called a left-handed table. I know in the video, he talks briefly about a middle table where he takes values to the middle. I wish he hadn't even done this. I don't even want to talk about this middle idea. Ours is what's called a left-handed table, and I'll talk about that in a minute. All right, there's an example of your positive z-scores. Can't really see it all that well. And there's your negative z-scores. All right, first example. Precision Scientific Instrument Company manufactures thermometers. That's supposed to read 0 degrees at freezing point of water. It goes on and on and on, talks about this. Here's the key, Pisces. Assume that the mean is 0 and the standard deviation is 1. All right. Then I see that. I know I have a standard normal distribution. What is he looking for? He's looking for the probability that at freezing point of water, the reading is less than 1.27 degrees. All right, so I start out drawing my bell curve. There's my mean right in the center, right? Highest point is the mean. Well, if that's 0, and I'm looking for the probability of less than 1.27, 1.27 is obviously to the right of 0. Now, where you put it here, it doesn't make much difference. All you know, it's to the right of 0 because it's a positive number. Now, I'm looking for the value, the probability that my z or my x value, I'm looking for the area, all right? And z being the temperature is less than. Well, less than means go to the left. Less than. If it was greater than, I'd be going to the right. So it's from this vertical line. The area that's associated with this z-score is the area to the left. To the left. Left meaning this way, not going to the right. Left-handed table. All right, so we go to our chart. All right, positive z-scores. What I'm doing, I'm trying to find the value, the area that associates itself to 1.27. So I'm finding 1.2 along the left edge, and the remaining the 0.07. If I take these two, I get what I need, 1.27. And where this column and this row, sorry, where this row, I had it right the first time, where this column and this row intersect, I'm reading 0.8980. All right, so you're saying, not bad. Do I really want to do this for every problem? Well, we'll see. All right, so from the table, I'm reading that this area is 0.8980. That kind of makes sense because if I were to draw a vertical line here, this would be half, which would be 0.5000, and to the right of 0 would be point. So this is obviously more than half. I can kind of say 0.8980 kind of makes sense. Now, notice for negative infinity, I'm using this negative E99, and from the positive infinity, I'm using positive. And I'll show you in the videos how I do that. The idea is using the table, we found this area to be 0.8980. So what he says is, hey, 89.80% of these thermometers will have a reading that is below less than 1.27. How can my calculator find this answer? Well, what we're going to do is we're going to go back to that vase menu. We're going to go to second vase, and we're going to come down to number 2, normal cumulative. Now, he talks here about separating, the scores. That's for an 83. All right, for an 84, they'll prompt you for all the values. He's going to ask you for a lower bound and an upper bound. The lower bound is the low one to the left. The upper bound is the value you're looking for to the right. Sometimes the lower is negative infinity. Sometimes the upper is positive infinity. Sometimes you have a number for both of these. Lower to the left, your upper value to the right. All right, so my lower value here, I was going way out to negative infinity. I'm putting in negative E99. I'm going to my upper value, which is 1.27. There's my lower, there's my upper. Mean is 0, standard deviation is 1. All right, here again, play this video outside of this video of the PowerPoint. Play the video from the actual PowerPoint. You see exactly how I did it. All right, so first problem, we wanted to know the area less than 1.27. Now we're going in the other direction. We want to find probability that this thermometer reads greater than negative 1.23 at the freezing point. All right, so if I were to use my table, first of all, I would draw my diagram. There's my 0. Negative is to the left of 0. I'm looking for the probability of the score, the reading being greater than. Well, greater than means to the right. But here's the deal. Here's a common mistake people make. They go to their chart and they look up negative 1.23, and they're going to find they're going to find this answer here. Excuse me. Remember, this is a left-hand table. The area that's associated with this value is the area to the left. All right, it's this number right here. You look up this in the table, you're going to find that number. You're looking for the number on the other side, the area from here to the right, greater than. So to find that, you're going to take 1, subtract what you have here, and there's your correct answer. All right. Remember, a left-handed table, the area that's associated with that number is the area to the left, this way, not the other way. So, you see a number, you put it in, automatically, the calculator's going to give you the right answer. Now, you got to do some thinking here. It's a left-handed table. All right, so looking this up in the table, negative 1.23, there's the area I subtracted from 1. There's my correct answer. All right, this is how I did it. There's my negative 1.2. And there's the remaining 0.03, and that's how we came up with an answer of 0.1093 for that area to the left, and we subtracted it from 1. You can see, using the charts, it gets to be a little cumbersome after a while. Thank God for a calculator. And there I show you how to do it on the calculator. Just be aware there are going to be times as we move forward, you're going to know how to use the calculator. Reason being, the answers are going to be, you're going to have some slight discrepancy. What you're going to notice is it's not always the answer that's closest to. So we'll deal with that when we deal with that. All right, the last option, we went to the area to the left, we went to the area to the right. The last option is when you want to find the probability of the area between two values. All right, here's the case. I would go to my chart. I look up the area that's associated with 1.50. That's from here all the way to the end. I would look up the area that's associated with negative 0.20 from the table. I would find the area from here to the end, all the way to negative infinity. Then I would subtract those, and that would give me the area that's in between. All right, so these, if you're using a table, require looking up two values and doing some subtraction. But notice, here's the answer, 0.9104. If you had an answer like, say that this area was like 0.162, you're saying, this is a good chunk of a curve. It's going to be pretty darn close to 1. All right, so there's how I do it with the calculator. Your lower limit is your upper limit. It can't be any more straightforward. But once again, I'll caution you, draw the diagram. Make sure you get a notebook with plenty of space, plenty of paper. Drawing a bell curve isn't going to be the hardest thing you're going to do in life. Here's a chart talking about different ways of finding, and you'll see here the symmetry. This area and this area are one and the same. Z-scores, one's negative, one's positive, but the areas will be exactly the same. Here's how you do the one in between, where you find the area from here all the way back, and then find that area and then do the subtraction. All right, so two problems here. This is the area to the left, this is the area to the right, and I'm only going to do number 11 on YouTube. And I'm not going to use the chart at all, even though as you go through the PowerPoint, you're going to see how they did it with the charts. In other words, it'll show you the two answers, and you either subtract from one or not subtract from one, or find two values and subtract them both. We're going to cut right to the chase. The calculator's there. I'm not going to play pretend that it's not there. But be aware that at some point in time, you're going to need to know how to get this without your calculator. So that's the first one that I do, the second, and the third. And that's how they did it with the chart. You may want to practice this. Take a look at these. Find out how he did it with pencil and paper. I'm going to stop it right here because we're going to move on next time to inverse normal. As is the case in math, go down one road and then they flip the script and come back the other road. I've been giving you z-scores. You've been telling me areas, which are probabilities. We're going to flip the script. I'm going to give you the area, then you're going to tell me the appropriate z or x score. Because once again, when you have a standard normal, z and x are one and the same. So hopefully this helps, and I'll see you on the other side where I continue on with inversion.